Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at secants. So we're going to start off by looking at the curve y equals x squared, not a complicated curve by any means. But if we were to find its gradient, that is a bit complicated. See, over for this region of the curve, the function's increasing. What I mean by that is, as we're going to the right, as x value is increasing, the y value is also increasing. So here, the gradient, which I'll call m, will be positive. On the other hand, if I look over here, the function is decreasing. So as we have x increasing as we're going to the right, y is actually decreasing each time. That means the gradient in this region would be negative. The gradient here is going to be around 0 because as x is increasing, the graph doesn't seem to be going up or down much at all. It turns out that for y equals x squared, the gradient is different in different regions of the curve. It turns out that the gradient is actually different at every single point along this curve. So finding the gradient would be tricky. So how can we get around that? Well, we like to use lines. Lines are really easy when it comes to gradient because they have a constant gradient. Now, a line that intersects a curve more than once is called a secant. So this blue line here is called a secant, and we can use it to calculate the gradient of this curve. So what we need from the secant, we need it to go through the curve at 2 points because we can easily find the gradient of a line if we know 2 of its points. So this secant intersects the curve at 0, 0 and also at 2, 4. So the gradient of this secant is really easy to find. It's just 4 minus 0, y2 minus y1 over x2 minus x1. The gradient of this secant is 2. So what does that have to do with the red curve? Well, that tells us the average rate of change of the graph of y equals x squared between 0 and 4. Between these 2 points, on average, each time you go across 1, you go up 2. So that's the average rate of change, but you might, or hopefully, are thinking that this secant doesn't actually look like the curve. It's not even going in the same direction as the curve at this point 2, 4. So when we're looking at differentiation, we're going to be looking at how to find the gradient of the line at each of these different points. The problem is that lines like this don't give a good indication. They don't represent the curve well. So what will end up happening is that as we move the 2 points closer together, the gradient of the secant will much better represent the curve. Now we can see that easily. If instead of choosing this point here and this point here, what if I chose this point here and the point 2, 4? Suddenly the secant that goes through there is starting to look a lot more like the curve in this region. So the secant, it allows us to calculate the average rate of change of a function. Now we know how to find the gradient, but I'm going to give you a formula that looks much more like the formula we use in calculus. So this is the formula here in black. Now note that delta x, so that triangle is read as delta, means change in x. It looks like a very complicated formula, but it's actually just the 2-point formula. See, what we do is we find 2 points along the curve. One of them we call x and f of x. So that just means the function evaluated at this value, and delta x is the distance along the x-axis between the 2 points. So the next x value is going to be x plus delta x, and so the function evaluated at that point will give you the y value. So using these 2 points here, we're just using the 2-point formula y2 minus y1 over x2 minus x1. Now we can simplify this formula a little bit because x minus x is just 0. So this is our formula here for the rate of change, the average rate of change of a function between 2 points, which is the same as the gradient of the secant. So for our blue line here, note delta x was 2 because between this point and this point, the distance along the x-axis, the change in x values was 2. All right, let's now look at another example. So we're going to calculate the average rate of change of this function around x equals 2 with delta x equals 0.02. It might sound complicated, but it's actually really easy. What we're doing is we are calculating the gradient of the secant that passes through x equals 2 on this function, but also where x equals 2.02. So this is the formula we saw on the previous slide. So here we have f of x plus delta x, 2 plus 0.02. It's going to be f of 2.02 minus f of 2, all divided by delta x, which is 0.02. So to calculate each of these, just substitute the value into that original function. So f of 2.02 is 2.02 cubed minus 2.02, which gives us 6.222408. F of 2 is just 2 cubed minus 2, which is 6, and that's all divided by delta x. So putting that in the calculator, we get 11.1204. That is the average rate of change of this function between these two values. Now, because delta x is small, this should give a pretty decent approximation to what the curve is doing between x equals 2 and x equals 2.02. The closer together the 2 points are, the better the secant will approximate the curve in that neighborhood. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.